Welcome to The Explainer. All right, let's dive right in. Today we're going to tackle a concept that is the absolute bedrock of calculus, the precise definition of a limit.
Now, you've probably heard this before, right? This intuitive idea of a limit, that feeling of getting closer and closer to some value. And look, it's a great way to start thinking about it, but as we're about to see, it's just not the whole story.
But here's the thing. For mathematicians, words like close and approaches, well, they're just too fuzzy, too vague. You can't build something as powerful and as reliable as calculus on a foundation of kinda close. You need absolute certainty.
So, the big question is, how do we make this idea of closeness precise? How do we turn that fuzzy, intuitive feeling into a concrete, provable, mathematical fact?
Okay, so let's try to make this concrete. We can actually turn this vague idea into a specific kind of precision challenge. Instead of just saying close, we're going to demand a specific level of closeness and see what it takes to get there. All right, check this out. Let's take a really simple function. f of x equals 2x minus 1. Intuitively, it seems pretty obvious, right? As our input x gets closer to 3, the output f of x should get closer to 5. You can even plug in some numbers to check. 2.9 gives you 4.8, 3.1 gives you 5.2. Yeah, seems to work.
But seems to work isn't good enough. Let's get really precise. I'm going to set a specific error tolerance. Let's say I want our output to be within 0.1 of 5. No more, no less. So the question is, how close do you have to get x to 3 to guarantee that happens?
And we can actually solve this with some pretty basic algebra. The distance from our function's output to the limit, well, that's just the absolute value of 2x minus 1 minus 5. A little simplification, and that becomes 2 times the absolute value of x minus 3. And we need that whole thing to be less than our 0.1 tolerance.
And boom, there's our answer. The distance from x to 3, which we write as x minus 3, has to be less than 0.05. So what does that mean? It means as long as you pick an x that's between 2.95 and 3.05, but not 3 itself, that part's important, you are absolutely guaranteed that f of x will be between 4.9 and 5.1. We did it! We found a concrete answer!
And notice the pattern here. The tighter we make the requirement for the output, like if we demand it to be within 0.01 of 5, then the tighter our window for the input has to become. It shrinks right down to 0.005. There's this direct relationship between them.
This relationship, this back and forth, is really at the heart of the precise definition of a limit. And you can actually think of it as a game, a kind of challenge and response that gets to the core of what a limit truly is.
So let's meet our two players. First up is epsilon, the Greek letter epsilon. Think of epsilon as the error tolerance, or the challenge. And on the other side, we have delta, or delta. This is the input range, or the response. Epsilon throws down the gauntlet, and delta has to respond.
Here's how the game is played. Player A starts by choosing an epsilon, any positive number they want, no matter how ridiculously tiny. Then, player B has to respond with a delta, a corresponding range for the input. Player B wins if for any x you pick inside that delta range, the output is guaranteed to fall within the epsilon range. And here's the crucial part. If player B has a winning strategy for every single possible epsilon, the limit is proven.
This whole game is basically what 19th century mathematicians like Cauchy and Weierstrass formalized into the official, precise definition of a limit. And this was a huge deal. It brought a whole new level of rigor to mathematics.
Okay, deep breath, here it is. I know, it looks like a bunch of symbols and it can be a little intimidating at first, but honestly, it's just the rules of the game we just played, written down in the formal language of math. Let's just break it down piece by piece. See? It maps perfectly to our game. For every epsilon greater than 0, that's player A's challenge, there is a number delta greater than 0. That means a response from player B must exist, such that if x is within that delta range, well, that sets the input conditions. Then f of x is within epsilon of L, and that's the win. The output is guaranteed. All right, so now that we know the rules of the game, let's see how we can actually win it by proving a limit using this very definition. We'll do a simple proof to see how it all works in practice. So here's our challenge. Prove that the limit of the function 4x minus 5 as x approaches 3 is 7. Our goal is to find a winning strategy, a formula for delta in terms of epsilon that will work no matter what our opponent throws at us.
Okay, so we always start with the win condition.
We want to make the distance between our function, 4x minus 5, and its proposed limit, 7, smaller than whatever epsilon our challenger chooses.
So now we just do a little algebra. Inside the absolute value, that simplifies to 4x minus 12. And hey, we can factor out a 4, right? So now we have 4 times the absolute value of x minus 3. And this is the key. We've isolated the term that represents the distance of our input from its target.
And this right here reveals our winning strategy. All we have to do is set our delta to be epsilon divided by 4. That's it. So if our opponent challenges us with an epsilon of 0.01, we just respond with a delta of 0.0025. We have a formula that wins every single time. The proof is complete.
So you might be thinking, okay, that's a neat trick, but why go through all this trouble? Is this just a mental exercise for mathematicians? Not at all. This level of rigor is what makes calculus possible.
Because this precise definition is the solid foundation upon which all the rules of calculus, what we call the limit laws, are built and proven. It's the bedrock that ensures that when we calculate derivatives or integrals, our results aren't just hunches, they're logically sound. It's what turns calculus from a collection of intuitive ideas into a consistent, incredibly powerful system.
And it really makes you wonder, doesn't it? What other obvious ideas, in science or just in life, could be totally transformed if we applied this level of rigorous thinking? What new power could be unlocked by defining our terms with this kind of precision? Thanks for joining this explainer.